to our last leg of lectures in module 3 on finite difference method. Today's lecture is in continuation of what we discussed yesterday regarding computer implementation for one-dimensional heat conduction. So we'll proceed further and have a look at the actual implementation in a standard development environment of the pseudocode, which part of it which I wrote yesterday. So let's recap of what we did yesterday. We restated our heat conduction equation. We had a brief review of this solution process and summary of finite difference algorithms which we are going to use for solving this particular problem. And then we discussed what are required data structures and a part of the pseudocode for C and C++ implementation. So today's lecture is continuation of yesterday's, or the last lecture on computer implementation on finite difference method for steady state heat conduction problems. So we'll again have a brief look at what we did yesterday before we can continue further. So a statement of the problem, required data structures, and then we will have a detailed look at a C++ implementation in a free development environment called developer C++ IDE. So this was our problem statement. We are dealing with a 1D heat conduction problem with heat generation and constant thermal conductivity, and we said our code should provide for any combination of boundary conditions, that is we can have specified temperature boundary conditions, Neumann boundary condition, or convective boundary condition at either end, with some restriction on specification of both end Neumann boundary condition, which we should be aware of. Once again, our implementation would assume uniform grid spacing and CDS for discretization, and we should ideally provide for both vortex based as well as cell centered finite difference solution algorithm in our code, and provision for all types of boundary conditions. Our source term would be temperature dependent. That's what we had decided, and we said we are going to break our code into different modules for simple implementation. It is not just for the simplicity of implementation, it should also help us in testing each module separately before we can combine or synthesize in our final code. So we said we are going to develop a set of modules, one module for geometry and boundary conditions, another module for generation of the system matrix, and we will have one module for solution of algebraic systems, and then one separate module for output of boundary conditions. And then we said, okay, let's come up with required data structures, okay, and our decision was based on what are the input output parameters we require and the simplicity of the interface between different modules. Okay, so we decided upon few data structures. We said, look, grid, this is the one which is going to contain all the geometric information of the grid, the endpoints, the grid spacing, the number of divisions, the number of computational nodes, and material properties, that is thermal conductivity included there. Then we will introduce one more data structure which we call matrix, which should have the details about the discrete algebraic system which we get from finite difference discretization. And for boundary conditions, we will have different types of boundary conditions we might have at two ends. So let's have a new data type to hold this boundary condition information, the type of boundary condition and the pertinent data. And similarly, we assumed our source term to be temperature dependent, and primarily let's take a case of linear dependence, and we should support it by a separate data structure. And then we discussed our pseudocodes for some of the modules, that what should be the look, or what should our input module do, what should a system matrix module do. And in system matrix module we said, look, we should provide two submodules, one which takes care of the implementation of boundary conditions in case we choose our normal finite difference approximation, that is our vortex based approximations, and we should provide for a separate module or submodule for system matrix which can implement boundary conditions for the cell centered approach, and then one simple solution module and output module which should output the data in the modular format. So now today we are going to have a look at the code implementation of these modules starting from the pseudocode which we discussed in the previous lecture for the input, system matrix, and we will first take up the case of normal implementation or normal finite difference approximation and how do we implement the boundary conditions. Cell center approximations we are going to take up as a refinement to the code which we developed later on. Then we will assume for the time being that we have got a solver routine available to us based on tri-diagonal matrix algorithm. So we won't discuss this in detail, and then we will discuss our output routine. Okay, now let's have a look at the implementation aspects. So our code implementation. What we would do is we are going to separate what is referred to in programming parlance as separate the interface from implementation. So for this purpose what we will do is we are going to collect all data structure definitions and function prototypes in a user defined header file. So that's one thing which we will do, and the second decision we should make is let's keep the implementation of each module in a separate file. So keep implementation of each module in a separate file. Okay, and in each of these separate files we need to incorporate or we need to include user defined header file, in each module. The next programming decision which we would take is we are going to use variable size arrays or dynamically allocated arrays. So use dynamically allocated arrays for holding a system matrix and RHS plus solution vectors. So we are not going to limit the size of array statically, it won't be known at compile time, it would be allocated based on the number of grid nodes we would actually specify. So we are dealing with the multiple files. On Windows operating system we will choose what we call a project mode. So our choice of IDE, you can work with any integrated development environment available to you. I have chosen here developer C++, which is freely available, but the code which we developed should be independent of your IDE. So, this is what we refer to as portable code. So, the set of files which we have developed here, you can use it in any development environment. We choose Borland C++ or Visual Studio, Developer C++, Code Block or anything. You can take it on a Linux machine and you can use GCC compiler there by making use of a make file or just compiling all the files together, and it should work equally well. So, that is why we are not going to use any IDE specific features. We will restrict ourselves to use of standard language features. In particular, we will restrict ourselves to ANSI standard C++. For the sake of simplicity, I have chosen C++, but this code could be slightly modified to work entirely with the C compiler. We are not using any object oriented feature. Our code is entirely procedural. So, code is procedural. Okay, since we have broken our code into different files, so on Windows operating system and in our development environment, we would create a separate project in which all the required files would be included, and this would facilitate our job of compilation of the code and is debugging and running of the code. So, now let us move on. Let us move to developer C++ environment. Let us look at some simple features. If you wanted to start off fresh, open your development environment, go to your file menu and choose a project. And normally you will be given plenty of options. For instance, in developer C++ environment, yes, you are prompted for Windows application, console application, static library, DLL, and so on and so forth. On Microsoft Visual Studio, you might have slightly different set of options, but you should choose this console application option would be there. So, choose this console application option, choose your project to be a C++ project, choose the name, whatever name you want to. For instance, for our application, we have chosen a project with this name just called project 1, and there are various files which are included as a part of this project. Okay, now first let us have a look at our data structure implementations. So, we have chosen a header file which we have called FEM1D. FEM1D heat conduction.h. This is a user defined header file, and this is how this header file looks like. Whenever we define a header file, it is always advisable to include all the set of definitions within this if and end if block. So, if and if declare this constant FEM1D underscore HC. You could choose whatever name you want to choose for this constant. Okay. Normally we will choose the constant depending on our nature of the project. For instance, we are dealing with finite difference method solution for one dimensional heat conduction, so I have chosen the acronym fairly similar to that, FDM1D underscore HC. HC stands for heat conduction. So, if and if not defined, then define this constant FDM1D HC. Now, this if and has defined, these two statements will help us avoiding multiple inclusion of the contents of this file whenever we include this header file. So that's why we require that. Now let's have a look at each structure, or rather each data structure which we have we said we are going to define. The first one is grid. So we have used the keyword struct to make sure that all the elements or all the members are public members. We could have as well used class if you wanted in place of struct in C++ language, but these set of definitions would work equally well in C language as well. So that's the reason I have used this keyword struct to define new data type. So struct grid, capital GRID, following the convention that the first letter of a data type would be capitalized. Now as we discussed yesterday, what are data which we need, which would be part of this struct grid data type. So grids would have the two endpoints of a domain. So their coordinates are double XA, double XB, and we would provide comments here. Coordinate XA refers to coordinate of the left end, double XB this refers to coordinate of the right end. There is number of subdivisions or number of cell divisions in our finite difference discretization. So we used an integer parameter and div. We have assumed uniform grid spacing, so we can have only a single double value. Let's call this as dx, double dx. So dx is equal to xb minus xa divided by n div. That's how we are going to set it in our input routine. The number of computational nodes that will depend on our formulation. It would be one more than number of divisions in the case of usual finite difference formulation, and it would be equal to number of divisions in the case of cell-centered formulation. And that FDM formulation we will distinguish, or we will flag off using our integer flag FDM capital T by PE. Now this FDM type, it will be 0 for cell-centered finite difference scheme and 1 for our usual finite difference approximation. We have also included in this grid data structure our thermal conductivity. This was the only emitter property which came in, which was involved in our steady state heat conduction problem. So for the sake of simplicity, let's include this also in our grid data structure. Next, we have our BC type to hold the boundary condition information. So first member would be an integer type. So BC type 0 would stand for Dirichlet boundary condition, that is temperature specified. If user enters 1, that represents a flux, and 2 stands for convective boundary condition. So we have put all the required comments or documentation right here, that what this particular member or variable stands for, what would be specific use. Next, we would provide for the required data for boundary conditions. For instance, TB would stand for the specified temperature, QB for the specified heat flux, H for convective heat transfer coefficient, and Ti for ambient temperature in case of a convective boundary condition. And we will set these things appropriately in our input module. Next is our discrete algebraic system. We need a data structure for that, and remember our matrix was a tridiagonal matrix. So we need to store 3 diagonal elements plus our unknown vector and the load vector. These were the arrays which were involved in the definition of a matrix. So struct matrix, the first element is W star AE, which is pointer for FDM array AE, double star AP pointer for that FDM array, AP, that is to say our AP stands for the main diagonal, and AW stands for our lower diagonal. Next, double star B, this stands for, this provides the storage location for right hand side vector in the system algebraic system AT is equal to B, and T is our solution vector for temperature. Now these are all these arrays, like they are pointers which would be linked to dynamically stored created arrays of appropriate size. Similarly, we need a data structure for source term. So, source term, if we assume a linear variation or a source which depends linearly on temperature, we can have a linear relation Qg is equal to Qga plus Qgb. So, this particular data structure would store these two coefficients Qga and Qgb. So, struct source double Qga double Qgb. We will collect in this header file all the function prototypes which we would generate as a part of our implementation, so that these functions can be referred to in any module or in any file. So, first function is our void input, which corresponds to input module. It has got the parameters of like grid, boundary conditions and source term. Now, this grid ampersand, this ampersand reference to what stands for what we call in C++ as a reference type. And so, grid ampersand grid BC type, we will have two boundary conditions, that is why we need an array. This is an array of dimensions 2, and similarly a reference for the data Qgen. Similarly, we have also provided for a routine which will just print in the user specified information for cross checking purposes. So, again the parameters would be grid ampersand grid, BC type BCS and source ampersand Qgen. The next function corresponds to our matrix module, that is to generate or compute the matrix coefficient, and we need to provide as input the things related to grid spacing, number of nodes, material property and so on. We also need to provide matrix. In fact, this matrix ampersand m, we would get all our computed matrix coefficients or matrix entries. As input, we also need to provide the source term and the boundary conditions types. For checking our matrix which has been generated or matrix entries which have been generated by get matrix, we can have a print matrix function which will simply print out our entries, the matrix as well as right hand side arrays. Then we have decided to incorporate or to introduce two sub modules or two sub functions which will be called by our get matrix function. So, these two functions stand for two different finite difference approximations which are, or formulations which we said we would use. So, get BCS normal, this particular function stands for the case where we would choose our vertex based finite difference formulation, and it would modify the matrix entries corresponding to the boundary conditions at two ends. Similarly, for a cell centered formulation we can have a separate function which will do the same job. And the end, our last module was our output module. So, we will have one function void output, provide the grid ampersand grid, the grid information and the matrix information which contains our solution vector. So, this is our header file wherein we have collected all the data structure definitions and the prototypes of all the functions. I would just like to point out the names which we have used here, they are just dummy names. So, if you want, you can get rid of this, the name here grid, we can just simply have capital G or IDE ampersand, that should be good enough. So, all the names here are simply dummy names. In prototype we primarily need the type information. Okay. Now, next let us have our main or driver function. How will that look like? So, we have got our included statements, has include cstdlib in case we want to use some functions from standard C library, then usual C header, IO stream which provides for input output objects of C IO stream library using namespace std, so that all the standard library names are available to us. And we have to include our user defined header file which contains the definitions of all the data structures as well as function prototypes. So we have has include within double quotes FDM underscore 1D heat conduction dot h. This was the header file which we have generated. Since it is a user defined header file, we must put it double quotes. Next, for the solution purposes, we would use an external function. Okay, let's call it a TDMA, which incorporates our tri-diagonal matrix algorithm. We will discuss this in detail in our next module on solution of algebraic systems. So why TDMA? We need to provide the size int n provides the size of the system, and this AP, AW and AE, they refer to three diagonals. AP is the main diagonal, AW stands for the lower diagonal, and AE stands for the upper diagonal. Then B stands for an array which will store or write inside the vector, and we will get solution in vector u when this routine or this function returns. Now let's have a look at our main function or the interface which we will have here. So int main. First thing which we have to do is we have to define the appropriate data types. So grid, capital GRID, and let's choose the same name, grid, starting with small g. Please remember that C++ is a case sensitive language, so capital GRID and small grid, they are two different identifiers. So that's the reason why I have used this small grid as the name for our grid data. Next is BC type. BCS, let's call this bounded short form for boundary conditions, BCS. Within brackets 2, we have got two ends where boundary conditions are there, so that's why we need to provide, or we need to make it an array of size 2. Source QGen, this would hold the information about our heat generation term, and matrix M. Matrix for data structure, we now declare object of type or variable called M, which will hold our complete finite difference algebraic system. Remainder of the main, we are just going to call all the functions which correspond to different modules. Like for instance, let's call the input module. So input, name of this module is input, and we will provide these three objects as the parameters. So grid related information would be returned by the input function in the object grid. Similarly, boundary condition related information would be returned in this array BCS, and source term related information would be returned in this object QGen. If you want to cross check, so we can call input print. It's given input as grid, BCS and QGen. So it simply prints out all the information which have been input. In addition to that, it also prints out the number of computational nodes and the grid spacing. After input, we need to generate finite differential algebraic system. So call our matrix module, which is represented by a function get matrix. So get matrix, grid goes as input. So grid, QGen and BCS, these three objects are provided as input to this get matrix module, and then it returns the output, that is the assembled matrix entries AP, AE, AW and B. They are the arrays which are contained in this object M. So all those arrays taking care of the appropriate boundary conditions and the source term, they are all returned by your function get matrix. We can also print, before we proceed for solution, we can say that whether the entries which have been generated, the matrix entries, whether they are correct or not. So we can call a function, simple function print matrix, which will print the matrix entries corresponding to each node. Then solve a linear system using tri-diagonal matrix algorithm. So we will use this external function TDMA grid.n nodes. N nodes is the number of grid nodes, and then m.ap, this gives us our main diagonal, m.aw lower diagonal, m.ae upper diagonal, m.b is our RHS vector, and the solution would be returned in the vector m.t. And once we have got the solution, output it, print it in tabular form. So output pass these two parameters or objects as input, grid and our matrix M. Grid will contain the information about the number of grid nodes and x coordinates if you want to print that out of each grid point, and M would contain our solution vector as M dot T. So once it is done, return 0. This is where our main function ends. So if you look at the implementation of the main function, it looks very simple, very clean. So that's how we normally proceed in writing any code, any useful or what we practical code. We will not have the actual implementation of different functions in our driver program or what we call main function. Driver program will only act as a controller, and it will call different functions to help perform different set of actions. So input, generate matrix, call the solver, and call the routine to provide the output. That will be a typical structure for any CFD code. Now let's have a look at implementation of each module separately. So first let's go to our input module. Okay, has include IOStream, and I have just included CMath in case we might need sometimes some mathematical functions from C library using namespace std for standard input and output objects. And we must include the user defined data structure file in each of our modules. So has include within double quotes FDM 1D heat conduction.h. Okay, and this module we have put two functions, the main module which corresponds to function input and one function input print. Okay, let's look at the documentation. That's the usual coding approach, that we should provide few lines of comment as to what that particular function is going to do. Although this is not complete comment, maybe I should have also written what are these input things, grid, BCS and QGen. So there should be one line comment each in this here, that what does grid stand for, what is BCS stands for, what QGen stands for, and then it should provide a version that at which date the code was written, and if you want you can also write the name of developer. So this will help keep track of the changes which have been made to each module or function, so that we know of the updated features of each module. Now let's come to our actual function module. So void input, this particular module doesn't return anything via its return type, so that's why we have put return type as void. Everything returned through these parameters. So grid is a reference type parameter, grid ampersand grid. Please remember, if you remove this ampersand, that becomes what we call in C++ language as pass by value. So nothing will be returned back to your main program, we won't get anything out. So that's why this reference type is required. If you want to, instead of C++, you want to change to C language, you should instead change this reference to a pointer and create that pointer in the main function instead of an object called grid. Okay, the same thing, the same comment holds good for this source object, source type object QGen, that if you don't want to use references which are available only in C++ language, just change it to a pointer, so that should do a job. We have defined a local variable called bndry. This is an array, character array, just to for the sake of prompting the user whether we are at left boundary or at the right boundary for inputting the boundary conditions. Now the way I have written this module is for an interactive way. Okay, this can also be changed in a non-interactive fashion where all the input can be read from a file. So those modifications I think I would leave as a simple exercise. All that we need to do is just replace the cin by an appropriate file link object. The rest of the things should work in identical fashion. So we would prompt the user to input each type of data. So cout is this what it does. It inputs it, or it prints out a set of lines or set of characters on our console, that interdomain ends xa comma xb and number of cell divisions. This is the first input which we are going to prompt the user, and then user will input the data, and that data is stored in grid.xa, that's x left end, grid.xp the right end, and grid.ndev, that's the number of divisions. Next we can compute the cell spacing grid.dx, which is equal to grid.xb minus grid.xa divided by grid n division. I have put this FABS just in case if the user enters the things in a different order, it enters the right coordinate first and left coordinate later, so that can be taken care of because grid spacing has always got to be a positive number. Then we prompt the user to enter what we call finite difference or FDM type, whether we are going to use usual formulation, so input 1 for the usual finite difference and 0 for cell centered ones. So C in grid.fdm type. Now this choice of 1 and 0 was made with a specific purpose. In our usual finite difference formulation, vertex based ones, our number of grid nodes is 1 more than the grid divisions. So if you put here number 1, the number of grid nodes is simply grid.ndev plus 1, and for cell centered the number of grid nodes is equal to number of divisions, so this 0 works pretty well here. So we need a single statement here, so grid.n nodes is equal to grid.ndev plus grid.fdm type. Then prompt the user to input the thermal conductivity, so C in grid.k, and then we have to prompt the user for boundary conditions at both the ends. So let us use a simple for loop for int I is equal to 0, I less than 2, I plus plus, because we would store our boundary conditions in an array of length 2. The first BCS 0 would hold the boundary conditions at the left end, and BCS 1, that object will hold the boundary conditions at our right end. So let us prompt the users, C out input boundary condition type at the given boundary node. The first data which would be input is BCS.type, and once this BCS.type has been entered, we provide some default values. BCS.type could be anything, it could be 0, 1 or 2, that is Dirichlet boundary condition, Neumann boundary condition or convective boundary condition. So let us just initialize these values because this TB, QB, H and TA would not be specified by the user for each type. User would specify only the required information. So now let us provide some default values to all the parameters, default value of 0. So BCS I.TB is equal to 0, QB is equal to 0, H is equal to 0 and TA is equal to 0, and then depending on the type, if type is equal to 0, that is Dirichlet boundary condition, we will prompt the user to input the specified boundary temperature and read it in BCS I.TB, else if the boundary condition type is 1, that is the flux is specified, so ask the user to enter the specified boundary flux. So C in BCS I.QB, else if BCS type is equal to 2, that is to say it is a convective boundary condition, so prompt the user to enter H and TA values and read them in BCS I.H and BCS I.TA. Now please be careful while writing a program. So BCS I.type, for testing equality in C++ or C language, we have to provide two equal to signs. Don't just put a single equal to sign. Single equal to sign stands for assignment. Okay, so if you put a single equal to sign, that will lead to an error, a logical error. There won't be any compilation error prompted by the compiler, but your program won't work correctly. So now we have input the boundary condition data. Next we need to input the source terms. So prompt the user, prompt the message that in what form we expect the input to be. So assume heat generation rate is expressed as Qg is equal to Qga plus Qg multiplied by T, that is a linear variation of temperature, and then ask the user to enter Qga and Qgb in that order and read it C in Qgen.Qga, which will contain the constant part of the source term, and Qgen.Qgb, which will contain the coefficient of the temperature term. Okay. So and thereby that finishes our input module. For the testing purposes, we can just print our input in a tabular format. Okay, so we can just have this testing routine which will print the input data, void input print, pass the grid object BC type and source gen, and let it print it in nice tabular format for us. Print the grid ends, number of divisions, FDM formulation type, number of grid nodes, grid spacing, and so on. Print the thermal conductivity, print boundary conditions, print the source term. Okay. So now the collection of these two routines that completes our input module, which will read the input data for us, and it will also provide the printout of the input data which has been entered by the user for a cross check. So we can make sure that we have entered all the data correctly. Next, let's proceed to our matrix module. So once again, we have included this header file FDM 1D heat conduction.h, and let's put a comment here saying its function. So this function get matrix, in this module we have put this function get matrix, which will allocate all the arrays which are part of our data structure M. So it allocates, initializes, and computes the entries of the system matrix A and right hand side vector B. It also allocates memory and initializes our solution vector T. So let's put the version and date. Now let's have a look at the implementation. Once again, return type is void because we don't need a single data to be returned here. So let it be void get matrix or mod function name. The first parameter is a reference type parameter, grid ampersand grid, which is an input to this module. Matrix ampersand M, this is where in the output from this mod would be returned. Source ampersand QGen and BC type BCS, they are again our inputs to this module. In our standard commercial codes, we would put keyword const before these input only parameters grid, QGen, and similarly this array BCS, because this particular function is not supposed to change these. So if you want, you can put this keyword const here. So that will ensure that no modifications are made to grid data or source data or boundary conditions data inadvertently by this module. Okay, so the first task which this module is supposed to do is allocate this space, because all the arrays which are part of M data structure, they are all dynamic arrays, so we need to allocate space for them and initialize them. Now let's introduce a local variable int nx is equal to grid.nnodes plus 2. We have added this plus 2 for a specific region. Index 0, all the matrices in C or arrays in C or C++, their indices start from 0, but that 0 index we are not using here. For grids we have followed a standard format 1, 2, 3 and so on, and in the case of say we will go up to n plus 1. Okay. So what we should do is we should provide the size of our allocated arrays to be slightly larger to take care of the first 0th entries. Let's provide for an additional ghost node to the right. So that's why this additional size of plus 2 has been provided here, and we would use simple new operator available in C++. So m dot a is equal to new double within square brackets and x. What does it do? It creates space, memory space, which can hold nx double entries, and the address of that memory space, which will represent an array, is returned and stored in this pointer m dot ae. Okay, so m dot ae now becomes a dynamically allocated array of size nx. Similarly, m dot ap is new double nx, m dot aw, m dot b and m dot t. They have all been dynamically allocated. Next is let us initialize this. This initialization is very important. We should provide initial values to all the variables which we use in a code. So now let us initialize them with some appropriate values. So AE, AP, sorry, AE, AW, B and T, these have been initialized to 0.0. AP I have purposely initialized as 1 because some of the algorithms use AP in the denominator while solving the system equations. So if it is 0, it might create some problems for us. So let us by default set all the values of the main diagonal as 1. Our next task is to compute the elements of system matrix M and right hand side vector. First we will do it for all the nodes, assuming all the nodes are interior nodes. That is what happens in a self-centered formulation, all the nodes are interior nodes. Even in normal formulations it does not hurt much, we have got 2 additional nodes to repeat the task, and we would modify the boundary node enters later by calling appropriate boundary modification module. So for sake of simplicity we have introduced some local variables, double dx which is holds grid dot dx, k grid dot k, qga, qgen dot qga, qjb, qgen dot qjb. The contribution which would be generated to RHS, QRHS is qga into dx divided by k. Remember there is no exponential operator, so we cannot have dx caret 2 to represent dx square, you have to type dx into dx in C or C++ language. Similarly, contribution for the linear coefficient or the coefficient of temperature in source term, that will also has to be incorporated in AP. So that contribution is qmat. Qmat is qgb into dx divided by k. Next, let us generate all the entries. So int I is equal to 1, I less than grid dot n nodes plus 1, so that we go from 1 to n nodes, I plus plus. AE and AW entries are minus 1. Now AP entry m dot API is 2.0 minus qmat, and m dot BI is equal to QRHS, so that is our right hand side. And next we need to incorporate the effective boundary conditions, okay, and we will call 2 separate functions or modules to do the task for us. So if grid dot FDM type is equal to 1, that is we are dealing with normal finite difference formulation, let us call a function called get BCS normal grid comma m comma BCS, else we will assume our default implementation to be a self-centered formulation. So get BCS centered, pass as input grid m and BCS. Now we will discuss these 2 functions in detail in our next lecture. We will look at the pseudocode first, and then how do we translate them in appropriate functions, and thereafter we will build up our code further and solve 2 example problems in the next lecture.